you have extensively used DOS interrupts, right? So what is this DOS interrupts do? Yeah. First of all, let's understand what is an interrupt. What is an interrupt? The microprocessor is a busy person. Microprocessor is a busy person. Always it does some task, right? Okay. So in between, if you are actually expecting some service from microprocessor, you need to interrupt it. That's a word interrupt comes here, right? So interrupt is this, right? Have you understood? Microprocessor takes an interrupt something like this. You will see, right? Undesirable interrupts are always not good, right? So desirable interrupts are always good. So you know about interrupt now. What it does, it tells the microprocessor that there is a service requirement from the microprocessor. That's all. What microprocessor do, okay, with respect to these interrupts, that is very important to understand it. Right? You interrupt microprocessor. Whether that interrupt has to be properly listened by microprocessor or accepted by microprocessor, and microprocessor has given its service to the interrupt user, that depends on the microprocessor. And the entire study of interrupt is what service microprocessor is giving whenever you interrupt the microprocessor, right? But definitely, you know, there are any type of services required by the microprocessor, yes or no? Right? You have keyboard input, you have display, right? See, a requirement of a person can be anything, right? Somebody want water, somebody want chocolate, somebody want, many requirements. You say, sir, I want chocolate. You are interrupted me for the chocolate, right? Somebody say, most of the time, I got a phone call, I want to go to washroom, right? All those things are different reasons for interrupting. Yes or no? Like that, for various tasks, okay, to be performed by the microprocessor, each and every task has been given one number. It's called vector number, interrupt vector number, right? Like DOS interrupt, all the DOS interrupts have been given an interrupt number of dash. What is that? 21. All DOS interrupts are 21, right? Similarly, you have interrupt 10. Yes or no? For date setting or time setting, you have different interrupts. Have you seen that? You have all done that in your laboratory. Yes or no?
Yes.
Right? So interrupt is to interrupt a microprocessor. Why we interrupt the microprocessor? Because we want to get some service from the microprocessor. Which service? That depends on a number along with the interrupt. That's called as interrupt vector number. Right? What microprocessor do? Microprocessor will give its service. In what way microprocessor give its service? What way we can extract the service from microprocessor? By some program, yes. How does microprocessor functions? By using program only, right? Suppose if I want to get service from microprocessor by interrupting it, that means I'm executing some program. That is called as interrupt service routine. That's called as interrupt service routine. What it does? Very simple. You try to understand this enough. You have this 8086 microprocessor. You are interrupting the microprocessor. I'm just writing just a block diagram by giving interrupt number. Okay, I'll say interrupt 21. I'm interrupting, that means this is something to do with the DOS interrupt. That means I need to enter a data from the keyboard. What immediately microprocessor does is, whatever program a microprocessor is executing during that time, right? It will actually stop doing that. Stop doing that means its current address will be pushed to the stack, right? Then a service routine, it's like a subroutine, which is called as interrupt service routine, corresponding to this interrupt 21 is executed. This is nothing but, this routine nothing but taking a input from the keyboard. A program to take the input from the keyboard and save it in AL register. Yes or no? That routine is written in inter-service routine. Once it completes the inter-service routine, that means there is one written statement here. Okay, it will go back to the place where it was actually executing the program. I've understood this. Okay, so I'll repeat once again what microprocessor does during every interrupt. That microprocessor, assume that it is actually executing this program. Okay, executing this program. When the microprocessor is executing program at this point, suppose your instruction pointer, your CS instruction pointer may be 1, 2, 3, 4. Okay, this is your IP. This is your IP. So your microprocessor is executing this. Okay, IP corresponding to, it's a instruction pointer with the address where microprocessor is executing that instruction. Okay, so moment, assume that at this time one interrupt has come. Okay, there's an interrupt request to the microprocessor. What it does, it will keep the next address, it will push the next address to the stack, right? Then what is loaded in IP is the IP of this interrupt service routine. Microprocessor will start executing this interrupt service routine, for which the service is asked, right? So once interrupt service routine is done, okay, definitely whenever there is a subroutine, there's a return statement. Yes or no? You all know about it, right? Once return statement is executed, it will pop the address which it is pushed into the stack and then start executing from the next instruction. You have already done this in the program, right? Yes or no? Yes or no?
Yes, sir.
Right? You have done move AH, 01, interrupt 21H, right? What happens at that time? Same thing happens. And that interrupt 21H is for DOS interrupts. There are various DOS interrupts available depending on the content of the AH register. Okay, you will have different functions of the DOS interrupts. That is what interrupt is. Have you understood this? Okay. Now let us know something more about this interrupts. Hope all of you understood about interrupts. Okay. If you understood about interrupt and role of interrupts, I told you one of the example I told you because keyboard interrupt, because you all know about keyboard interrupt. Okay. So what are different types of interrupts available in the 8086 microprocessor? These interrupts are divided into two categories. Okay, two categories. One is hardware interrupt. Okay, another one is software. What is this hardware interrupt and software interrupt? Very easy to understand. What is hardware interrupt and what is software interrupt? Okay, in 8086 microprocessor, you have two pins. Can you see here? Three pins, totally three pins corresponding to interrupt. One is non-maskable interrupt, another one is interrupt pin, another one is interrupt acknowledgement. Right? There are three pins corresponding to interrupts only in 8086 microprocessor. right? There is non-maskable interrupt, INTR pin, interrupt pin, and interrupt acknowledgement pin. We have already discussed about these pins in brief. Okay, the function of these pins are nothing but interrupting microprocessor. Okay, see here, non-maskable interrupt. Non-maskable interrupt. What is a non-maskable interrupt? This is an external input applied, which is called as non-maskable interrupt. See, this non-maskable interrupt is something which cannot be masked. What is this masking? See, whenever you interrupt a microprocessor has an option whether to acknowledge that interrupt or not to acknowledge that interrupt. It's left to microprocessor, right? While programming, when such and such interrupt comes, microprocessor can be programmed in such a way that it won't accept that, it won't acknowledge that interrupt. That's also possible. I've understood this. Okay, like you have in bank checks. Whenever you give a checks, right, you say so and so check number, give stop payment, something like that, right? It is possible that microprocessor will not acknowledge, but this non-maskable interrupt is non-maskable. That means microprocessor cannot say that I cannot accept the interrupt. It's like emergency. Microprocessor has to accept the interrupt. If at all any interrupt is given through this pin physically, whatever interrupt service routine required for this, that non-maskable interrupt, microprocessor has to execute. No other microprocessor cannot say that I am not going to do this. Have understood this? Okay, that's called non-maskable interrupt, especially power failure. Whenever there is a power failure, okay, the signal of power failure is connected to non-maskable interrupt, right? So microprocessor has to do some routine whenever there is a power failure, right? It has to save some data, whatever is possible to do during power saving, it will do, right? Microprocessor cannot say I will not do, I can't do it. That's called non-maskable interrupt. This interrupt cannot be masked. Have you understood about non-maskable interrupt? Now, this is the hardware pin once again. This is the hardware pin. It is coming under hardware interrupts. Okay, there's one more interrupt called INTR. INTR is the pin. Okay, whenever you give high to this pin, see both are high, right? There is no bar here. Since there is no bar here, it is active high. Whenever you give high to this pin, signal high to this pin, that means you are actually asking microprocessor to interrupt and execute an interrupt service routine, right? Okay, now this interrupt is maskable. That means it is possible that we can program microprocessor in such a way that whenever high signal comes here, with some vector number, same time vector number also will be loaded to this. I told you vector number, what is vector number, right? See, this microprocessor can be interrupted for many purposes, right? Many purposes, right? So every purpose will have some number. How does microprocessor understands that it is keyboard only, right? It is because of the number. 21 is the number for DOS. Like that, this interrupts, there are 256 numbers are possible for this interrupts, for this 8086. So if at all a particular number comes, okay, we can program the microprocessor in such a way that it won't give any acknowledgement at all. That means it is not acknowledged, that particular interrupt. Have understood this? Okay. Whenever you send high signal to this interrupt, right, with some interrupt vector number, okay, if that vector number is accepted by microprocessor, it will send a low signal in interrupt acknowledgement pin. Can you see there is one interrupt acknowledgement pin here? It will send a low. That means it will accept whatever the key press from the keyboard. Okay, that particular interrupt service routine is executed. which does the acceptance of the key pressed to the AL register. Have understood this? Okay. Otherwise, it won't execute that. That's called maskable. You can always have an option of masking the interrupt whenever you give this, but non-maskable interrupt cannot be masked. Remember this. These are very important, right? Okay. So these are the three hardware pins responsible for interrupts. Now, there is an option for the software interrupt also. And one thing remember, hope you remember, there is a flag called interrupt flag in flag register, right? You know about flag registers, right? What are the flag registers available in 8086 microprocessor? Do you remember it? You have carry flag, auxiliary carry flag, and then you have parity flag, right? So many flags are there. One of the flag is interrupt flag. So moment a high signal is given to this, okay, and it produces, it will automatically, your interrupt flag will become 1. Your interrupt flag will set, from which microprocessor will understand that there is an interrupt coming in. So interrupt flag is also very important for this, right? So the setting and resetting of interrupt flag will go through this. I've understood this, okay? This is about hardware interrupts, right? Now, similarly, there is something called software interrupts. The one which you have used in your laboratory, it's called software interrupts. You are actually writing right program, right? It's called software interrupt, okay? So when you execute interrupt instruction, when you execute interrupt instruction with some number, which is called interrupt vector number, that's a part of a software interrupt, right? Okay. And one of the use of that is exception in program execution. Exception, right? Exception. I think in C++ you have heard about exception handling, right? The same one. Okay. There is one more interrupt called trap. Trap is also one of the interrupt which is used during the emergencies, or which is also used during your debugging. You have done debugging, right? Have you done debugging? In the first few programs, you have done, every time you are pressing F7 or something, right? It is nothing but an interrupt only. You are interrupting, you are telling microprocessor that you just stop execution. It's called single step execution. I think you heard of single step execution, right? Even in C++ also you have that single step execution. And in 8086 programming also you have done single step execution. And that single step execution, every time you are using this trap. Okay, I have understood this. Okay, so from this you have understood what is hardware interrupt and what is software interrupt, right? Okay, so hardware interrupt is exclusively these 3 pins. Software interrupts exclusively executed whenever you have interrupt instruction executed, right? You have widely used in throughout program interrupts, right? For example, instead of interrupt 3, right? Interrupt 3 is actually for stop executing. Similarly, you have another, you can use DOS interrupt also by putting 4C into age register, just call interrupt 21. This is also same. These two does the same task. Both of them do the same task. Okay. Okay. Now I have already told you this, right? The operation of an interrupt is similar to call. I told you, right? Similar to call, right? So you are actually telling the microprocessor, interrupting the microprocessor, and then microprocessor will execute one subroutine during that time, which is called interrupt service subroutine. It's called ISR, interrupt service routine. It does a similar task of a call instruction, but their call is not an interrupt. It's a sequential execution. But here it is an interrupt. Have understood this? Okay. Every interrupt actually has some tasks to do. Otherwise, why you interrupt? Right? That's why it is similar to call. Okay. What it does? Processor first pushes the flags. Right? It pushes the flag. What pushes the flag? Whatever the flag register content before the interrupt, it will push into the stack. Right? Now, immediately, see here, immediately your trap flag and interrupt flag is cleared. Tell me why it is we need to clear that. Once microprocessor comes to know that it is interrupted, interrupt flag will become 1, right? Right? And after that, it will make the interrupt flag 0. Why? Because for the next, because if interrupt flag is 1, microprocessor will not take any other interrupts. We cannot actually afford to keep that interrupt flag permanently 1. Right? So it takes the interrupt, okay, it considers it, immediately it does interrupt flag 0, so that for the next interrupt it's ready for the next interrupt. That's the purpose of this. I understood this. Okay, that's why your trap flag and interrupt flag is clear. Next, the processor pushes the current CS component onto the stack. See here, I told you, current code segment and instruction pointer, it will be more pushed to the stack. Okay, then it branches to the interrupt service routine. Have you understood this? Is it not same thing is happening in call instruction? Yes or no? Right? Imagine that you are executing this instruction. For example, move AX, BX. Okay, move say AL, BL. Some instruction you are using move SI, 00. Okay, 00. Now suddenly here you have interrupt 21H. Move AH, 01H. Right? Now see here, your microprocessor is executing this statement. It will have some CS and IP, yes or no? Come on. Right? Now, when the microprocessor is executing this instruction, interrupt 21H, the CS and IP of this instruction will be stored in the stack. Right? Tell me why it should be stored in the stack.
So that we can continue from the same.
Exactly. See, moment in microprocessor executes interrupt 21H, it has to serve the corresponding interrupt service routine, right? Yes or no? Right? So microprocessor will now execute the instructions corresponding to the interrupt service routine of this interrupt 21H. That CS and IP is different from this. Once that service routine is executed, it has to come and execute from next instruction, yes or no? It has to execute this. For example, if you have AL, 02H, it has to come and execute this after returning from here. How does it remember that?
Stack.
It will pop the instruction, the previous IP, previous CS and IP, and then that will be loaded to IP, and it will actually start executing from the next instruction. Same process happens in call instructions also. You all know about it. Okay. So this is what happens when the microprocessor is interrupted. It's very easy to remember. Now, what is this interrupt vector table? I told you that the interrupt, all the interrupts are having its number. Okay, see here, interrupt number, interrupt 00H, interrupt 01H, right? Interrupt FFH, right? Okay, all these are interrupts. There are how many interrupts? Tell me, interrupt FF means how much? Come on, in decimal you tell me. 256 totally, right? FF is 255, correct. We are starting from 00. That means how many interrupts possible? How many interrupts possible in 8086? 256 interrupts possible, starting from 0 to 255. Right? There are 256 types of interrupt, and these interrupts are all given a number. All these are given number. Right? And also, okay, corresponding interrupt service routine also to be resided in some CS and IP. That's also fixed. I've understood this. Last person. Are you listening?
Yes, sir, I understood.
Close your laptop. Close your laptop. Okay. The corresponding CS and IP for every vector number is also reserved, is also fixed. For example, take interrupt 00. For interrupt 00, see, always you will have a physical address, right? For all the interrupt here, for all the interrupts here, it has got corresponding interrupt service routine. It's required, right? Yes or no?
Yes.
All these interrupts, it has. Why you are in between disturbing this class when you are interrupting it? Otherwise, don't come. Huh?
2 minutes of
You should finish everything and sit, my dear. Huh? While watching movie, you sit 3 hours, right? 1.5 hours you sit. Huh?
intermission.
Go. Fine. Every interrupt has its own interrupt service routine. And those interrupt service routine is stored in some code segment and some IP, yes or no?
Correct.
Right? That is what this interrupt table says. For example, interrupt 0. For interrupt 0, your instruction pointer is 00000. Right? And your code segment address is 00002. It's fixed. Have understood this? Okay. Similarly, for interrupt 1, your instruction pointer points to 00004. Now, what is the code segment? Code segment is 00006. That means the interrupt service routine of interrupt 1 is available in this code segment and this instruction pointer. So whenever interrupt 1 is asking the service from the microprocessor, right? Microprocessor will get its interrupt service routine from this code segment and instruction pointer. So every interrupts have got its own interrupt, right? Now, when you come to this last interrupt FFH, its corresponding IP is 003FCH. Corresponding code segment is 003FCH. So in this code segment and instruction pointer, the interrupt service routine corresponding to this interrupt interrupt 256 we say, is available. See, purpose of this entire interrupt table is to know where that interrupt service routine is available. Right? For example, interrupt 21H. Right? Interrupt 21H. So interrupt 21H has some IP and some code segment fixed for that. So moment microprocessor is interrupted by interrupt 21H, what is the CS and IP loaded? The one which is available from this table. I've understood this. I've understood about interrupt table. It's called interrupt vector table. So every interrupt has its corresponding instruction pointer and code segment associated with that. That's the place your interrupt service routine is stored in the memory. Right? So when the microprocessor interrupted, your instruction pointer and code segment is loaded with corresponding instruction pointer and code segment. I have understood this. What is written here is the physical address, right? Even though you have code segment and instruction pointer, which is represented by 16-bit and 16-bit, and ultimately what is going to memory is physical address, right? You know how to make it into physical address, right? I've understood this. Fine. Okay. Right. Okay. So this is about interrupt table. Okay. What the interrupt table says? All this interrupt table gives you the code segment and instruction pointer corresponding to the interrupt service routines, which has to be executed by a microprocessor whenever that particular interrupt is executed, called or executed. Understood this, okay?
Sir, sir, all the instruction service routines will have how many 0 to 2, so it will store the service routine.
Exactly. After that offset is there. Now you have offset. You have all are in the different code segment, right? So one code segment can have 64 kilobytes of offset, right?
But this is already 20 bits physical address.
See, this is in the code segment 2, right? In code segment 0002, after that you can have 64 kilobytes of offset, right? This code segment 000.
So this is already 20-bit address.
Correct. You can form a 4-bit of that, right? You can make it 2000, right? Understood this? See, whenever you have one code segment on one IP, right? So one code segment, for example, 0002, okay? That's a code segment. In that code segment, you can have offset starting from 00002 to FFFF. 64K possible in that, right? Similarly, take some other code segment, like 0004. There also you have 00002 FFF possible. Yes or no? So if it is same code segment, if all are same code segment, then it won't be enough to handle all 256 interrupts. I have understood this. It is available in different code segments. So you have enough space to write your interrupt service routines. Right? This is where your interrupt service routines are stored. According to this, have you understood this? Fine? Okay. Okay, this is what is vector number? Okay, I told you already about the vector number. You have interrupt 0, 1, 2, 3, 4, 5, 6, 7, 8 till 250. Right? So you have only 256 possible interrupts. Okay. Then definitely these numbers it's like very important, right? Suppose if there is a number, say in UAE, okay, number 1 great number, right? It's a big demand. Yes or no? Right? Number 2 great number, big demand. Number 3 great number, big demand. You all know about it, right? Okay. So like that, these vector numbers are all in big demand in microprocessor. Vector 0 reserved for some specific purpose. Vector 1 reserved for some specific purpose. Right? So vector numbers from 0 to 10 may be reserved by some people, some task. I've understood this. Okay? That's what the significance of vector number is. See, lowest 5 vectors, see here, are dedicated to specific interrupts. When I said that you have interrupts from 0 to 256, from 0 to 255, nothing is in your hand. You cannot take as you wish. Right? My dear, stop texting. Listen to me. Right? Fine. I can understand what you're doing. Right? Every student I can understand. We have that, micro, what you call it as observations. Right? I can say everybody what they are doing, but still we are quiet because we don't want to, any disturbance in the class. Right? Concentrate, which will help you. Okay. So every vector, as I said, that it has result. So vector 0 to some 5, see, lowest 5 means vector 0 to 4. Vector 0 to 4 is used for specific interrupts. We'll see what are those specific interrupts are. Okay. See, interrupt 5 to 31 reserved by Intel for complex processors. That means you can't use it. Intel has already put his flag out there. Say that, okay, I want this. Okay. Now, upper 224 interrupts, that is from 32 to 255, is available to use for hardware and software interrupts. See. That means till 0 to 32, till from 0 to 31 interrupt, those numbers are reserved. Right? But all numbers from 32 to 255 you can use. Anybody, anybody want to use it. You are free to use it. Right? Okay. So DOS interrupts are using 21H. The DOS interrupt. Right? All DOS operations, okay, disk operating system, DOS operations are making use of interrupt 21H. Right? Okay, these are the way your interrupt numbers are actually used. Okay. Next. What interrupt 0? Interrupt 0 is used for specific purpose, I told you. Why? When it is used. Divide by 0 interrupt. Whenever there is a divide by 0. Right? When you actually have any value divided by 0, you're going to get infinite value, right? Okay? It has to say, microprocessor has to say your value is, it has to give an infinite value, or it has to say an error. It has to say an error. That is by this. Okay. If the quotient is too large to fix into AL by AX, divide by 0, interrupt is invoked, and it will give you an error called as divide by 0 error. Even though today if you see the calculator since long back, okay, this divide by 0 error is there, right? In calculators you can see that. Okay, the same thing. That means it is all coming. It is giving an interrupt with the number 0 to the microprocessor, and microprocessor responds to that saying that that's the divide by 0 error. Okay. Similarly, interrupt 1. Interrupt 1 is for single step execution. Okay. Interrupt 1, always whenever you have pressed the F7 key when you are executing the program, right? It is actually every time executing the interrupt 1. Right? See here. What it does? Interrupt 1 is the single step interrupt. Interrupt 1 is the single step interrupt. Okay. If trap flag is set, 8086 will do a type 1 interrupt after every instruction is executed. That means it will say microprocessor that don't do it. That's also an interrupt. Right? That's also an interrupt. You're telling microprocessor to wait, also an interrupt. Right? So that is interrupt 1. Okay? And whenever interrupt 1, your trap flag is set. Okay? How does it work? See here, what it does. First, it pushes the flag into the stack. What the push F does? It pushes the flag into the. It also pushes the content of AX register into the flag. It also pushes content of AX into the flag. Whatever content of AX. Now, the stack pointer is moved to base pointer. See, stack pointer is moved to base pointer. See, what is there in push now? Tell me. When you do push F, okay, your all flag content, entire flag content, this will go to the stack. Right? Similarly, you are actually putting AX also into the stack. Whatever you have in AX register, you go to stack. Content of stack pointer is moved to the base pointer. See here. Let us take an example. Okay. Assume that stack pointer is pointing to 3000. Fine. Right? Stack pointer is pointing to 3000. Okay. Now, moment you push flag, what happened? Stack pointer will be decremented by 2, right? Yes or no? I told you stack operation. Remember the stack operation. Stack pointer will be decremented by 2 and flash upper and higher bytes will be stored in this 2FFFE and 300. Yes or no? Right? Okay. Now you see here, it will decrement the stack pointer by 2 and it will put this value. Yes or no? That's what I told you. Right? From the stack pointer. Okay. Now, after that, push AX. Can you tell me where AX will be pushed? Once again, stack pointer will be decremented by 2 and it will put the AH and AL. Yes or no? AL will come here, AH will come here. Yes or no? All of you know about stack operation, right? I taught you stack operation, right? Now, you can see push AX. So, now what is the stack pointer here now? Right, you know where is the stack pointer? You know where is the stack pointer points to? Okay, after pushing AX, you know where is the stack pointer pointing to, right? And you're going to put that into the base pointer. You're going to put that into the base pointer. I've understood this. Okay, now move the content of BP plus 2. Okay, move the content of BP plus 2 to AX register. Now tell me, what is the content of AX register? What is the content of AX register here? Exactly, flag only. Right? Flag only, right? Flag only. So here, your AX register will have a content of flag register. Now you see, you do OR operation. You do OR operation with the, you do OR operation of AX and 0, 0, 0, 0, 0, 0, 0, 1, 0, 0. Can you tell me what are you trying to actually check by making OR operation of AX with 0, 0, 0, 0, 1? Can you check this? Can you check this content and check the content of this 16-bit flag register? Which bit this 1 corresponding to? Trap. You're checking this program from here to here is to check whether trap flag is set or not. So this OR operation AX, okay, will check that your trap flag is set. After that, put this content of the BP plus 2 into the AX register, then pop AX and pop flag. Right? The entire code from here to here is to check trap flag. To check trap flag, you do this exercise of writing program. You understood this? Okay. Now, if trap flag is set, it will go to the, it executes that corresponding instruction in interrupt service routine, which is to hold the processor for until you get the next. Right? Okay. So we will continue this from this slide only in the next class. See, setting the trap. You are setting the trap here. Now tell me, this entire program, what it does is, this will set the trap flag. That's all. The purpose of running this program is to set the trap flag. I understood this. Okay. Right. See, interrupt 1 will make only your interrupt flag automatically to set. But trap flag will be set by executing this set of instructions. Right? See now, you see what exactly you're doing? You're trying to move this to X register, then you're doing pop X, AX, then you're doing pop F. That means what will happen, tell me? Whatever content of that entire flag register with trap set will go to the flag register. That means you can see after execution of this program, even though trap flag is not set, it will be set. It will be set. Have you understood this? Okay. So this is what it does for interrupt 1. Okay. So we'll continue from this class. I'm just recording this. We can see.